We're back! And in the last video, we ended up talking about Wohler. And we said that Wohler was very important because he really destroyed this concept of what we called vitalism. You know, vitalism, up until that point, we thought that living organisms made a certain group of compounds, and those compounds were called organic compounds. But Wohler went into the lab and he said, whoa, 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 wait a minute. I can actually make these organic compounds from scratch, and that's what we called synthesize those different types of compounds, or make those different types of compounds, and urea was the one that he focused on. So after that point, people realized that you did not have to have a living organism in order to make urea, so the definition of organic chemistry began to change. Now, if we want to talk about structure, and if we want to talk about synthesis, we can do that. But before I show you that, I think it's very important for me to give you the quote from Friedrich Wohler. And Wohler said, "I cannot, so to say, hold my chemical water, and I must tell you that I can make urea without thereby needing to have kidneys, or anyhow an animal, be it a human or a dog." I think that's kind of funny. I can't hold my chemical water. That kind of meant he was about to pee on himself. He was so excited he wanted to tell someone. And he was so excited that he was going to pee on himself because he made urea, which is the very common component of urine or pee. So I think that quote was kind of fitting from Friedrich Wohler, don't you? All right, so let's take a look at this mechanism in action, this synthesis step. So this is the target compound right here. This is urea. And this is what Wohler ended up making in a laboratory. Very simple molecule, very clean molecule, a very symmetrical molecule. And we'll talk about these different kind of pieces and parts of a structure a little bit later on in the semester, but this is the structure of urea that we're focused on. Now, this is what we would kind of always draw in a chemistry class, right? The sticks and the elemental symbols for the elements that we're using. And then over here is something that we would call a space-filling model. Meaning that if I computerize this thing and I want to think about 3 dimensions, the space that this molecule takes up, that looks a little different than just the plain old-fashioned drawing that you're seeing on the left-hand side. So very often we're going to toggle back and forth between these two views. So that's why you're seeing both of these up on the screen right now. They are the same thing. One is just a structure that you would draw in this class on every assignment and test and all of the other things that come along with it. And the other one would be a more 3D representation or computerized model. So this mechanism in action, I think, is kind of important for you to see because it actually introduces you to the synthesis world. And this is a large part of what this class will be about. How do I make something? And how do those changes happen on a chemical level in order to get there? This is what we're going to call the mechanism. This is kind of the steps that the reaction needs in order to go forward. So we're going to end up drawing mechanisms. We're going to end up drawing individual steps in our own creative way to show how reactions go forward. But we can computerize this as well, and that's what you're getting ready to see on your computer screen. All right, so here's NH4, OCN, and that is how it begins to move and change to give you urea. So as you can see, the only thing that's going on is that this NH4 is separating. It gives this part a hydrogen, and it says, listen, here's your hydrogen. I don't need this extra baggage. There you go. Whoop. And in it goes onto this molecule. Well, that NH4 now becomes NH3, and then this moves and it attaches to the center of that molecule. Now, you don't really see the third hydrogen because one of those is drawn backward on you, but That's computerization, right? Okay, so if we take a look at this step, or these steps that make this product, this is what we are going to be referring to as a mechanism. Now, we do not have computerized models of these mechanisms the whole entire semester that you are with me. All right, we're going to have to do this the old-fashioned pen and paper way. We're going to have to draw them out. We're going to have to write structures. We're going to have to draw arrows to show where things go and where things end up. But throughout this semester and throughout the class, whenever we discuss mechanism or the synthesis steps, this is what we are referring to. So off goes a hydrogen, in comes an incoming group that gets switched around, and we see another shift in that hydrogen that points backward that we can't really see in that depiction. All right, so this is what Wohler did in his lab. He said, I can make urea, I can make that from this ammonium salt, and because I can make urea, it did not come from a living animal. It didn't come from a living thing. It came from me in a lab making it from scratch. We have to go back and we have to redefine this term organic compound. And no more vitalism is going to be in play. So, you know me by now. I told you I like to show you faces. And here is Friedrich Wohler, 1800 to 1882. A fairly good lifespan, especially during the 1800s. He was 82 when he passed away. A German chemist, pioneer of organic chemistry. I told you, we kind of call him the father of organic in a way. He discovered two elements on your periodic chart, beryllium and silicon. He started teaching at the age of 28, and he also discovered that two chemicals could have the same formula. What? Yeah, that's right. Two chemicals could have the same formula. Well, that's weird, isn't it? I mean, didn't general chemistry kind of tell you, whoa, 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 when you do a chemical compound, it can only be a certain way with a certain ratio, and it has to be that compound? Well, yes, it does. So, for instance, if I wanted to write peroxide H2O2, it has to be H2 and O2 every single time, or it's not hydrogen peroxide. It is something completely different. That is the ratio that we are referring to, that general chemistry referred to back in the day when you took it. But here, Wohler, because he worked in the organic world, said we could have the same formula. So, for instance, a certain number of carbons, a certain number of hydrogens, and maybe a certain number of oxygens. And all of those numbers, if they're stayed constant, we don't change them. That ratio stays. These can hook up in a different way and make a completely different compound. This is kind of new, folks. We didn't really talk too much about that in general chemistry when you took it. You probably didn't. But now we are going to slap you with the concept that if I take carbon and hydrogen and oxygen, the ingredients to make a compound, and I keep those ingredients the same, in the same proportion, those ingredients could give me different products depending on what I do with them. So, for instance, water, flour, egg. I can make a biscuit. I could make a cake. I could make a cookie. Same ingredients, maybe the same amount, and depending on how I fix it, and depending on what I do to it, I can end up with different products in the very end. That is what this statement basically means. And Wohler, this guy, was one of the ones that really put this into writing the very first time. So not only did he go through and disprove vitalism, he did something even more important, and he gave us this idea or this concept of what we are going to refer to as an isomer. Iso means same, mer means unit, same unit. So this basically means same ingredients, they hook up in a different way, and that gives us a different compound because of that. All right, so let me go back to my writing pad, and at this point, we have now talked about organic in a little bit more detail, hopefully more detail than what you knew coming into the lecture at this point. But organic chemistry is now defined as the chemistry of carbon-based compounds. You know, I wrote this in a previous video that you watched already, but I think it's important to write it down again because that is what we are going to focus on. Now, organic, it does play a major role in the body, which is why if you want to go to pharmacy school, if you want to go to medical school, whatever kind of maybe a health profession requires organic chemistry, whatever degree route that you are trying to take, this is one of the reasons that they are wanting you to take organic, because your body is an organic being. Your body is a vessel of organic reactions, making organic products every single day that you walk, that you talk, that you think, that you see. All of that is driven by organic. Every bit of it. And organic chemists would actually say that organic chemistry is the most important. Not the gen chem stuff, not the analytical stuff, not the inorganic part of the house, but organic is where it's at. Because this is really how we breathe and how we talk and how we think, how we metabolize. Why is it that when I take an aspirin pill, it targets my headache? All of that is organic chemistry driven. Now, here's the issue. In organic chemistry, there are millions, folks, of compounds that we can talk about. Well, the good news for you is that we're not going to talk about millions of compounds throughout the semester. We're just going to kind of focus in on a few, and we're going to talk about a few things in organic, and we're not going to go crazy with it. It's not meant to do that, okay? But this field is quite diverse. Tons of different things going on at the same time. So it's one of those fields and it's one of those areas of chemistry that really does need specialization. And you're going to specialize in a certain area that you're going to focus on and learn a little bit more about instead of trying to absorb every single thing that comes your way. And that's just the nature of organic. And you're just going to have to be happy with that, folks. You have to be happy, or you're going to have to be happy with the idea that you're not going to know the answers to everything. It requires a little bit more reading, a little bit more work, a little bit more research, but you'll eventually get there. But there's no way we're going to talk about that many different compounds throughout this time. The other thing I want to talk about is why carbon. Out of everything on the periodic table, why carbon? Why is carbon so special? Well, that really plays into the location. You know, very often, if you're at the age, and maybe you're not, but there will be a time where you will look at hopefully a home to buy. You're going to be in the real estate market. You're going to go around, you're going to meet a real estate agent, they're going to show you some houses, they're going to show you, the blingy ones, and they're going to show you some ones that need a little bit of tender loving care to get them as fixer-uppers. But in the real estate market, you're going to hear someone say something to you, and that is the statement, location, location, location. Folks, it's all about where it's at. Okay? If you go through and you buy a home and that home is 2 hours away from where you work, in the middle of nowhere, with no access to running water, or for some of you, a cell phone service or high-speed internet, then we have a problem. That is not a very good location. Who's going to buy that house? It's probably one of the reasons it's so dirt cheap. But then you're going to run across a home, and that home is going to be in the perfect spot. High-speed internet, maybe in a community, and that's what you're after. Maybe it's 10 minutes away from work, so it's situated perfectly to where you need to be. It is perfect all around, and that's due to its location and its position. Carbon has that going for him. Carbon is perfectly positioned on the periodic table to be involved in organic chemistry. Now, is he the only one? Well, yeah, he is. That's how specific the location has to be. So in order for me to explain that, we need to take a look at the periodic table. So let me pull one up for you. So here's a version of the periodic table. Now there's tons of different ones that are out there. You might see something a little bit different attached to an assignment or a test that I give out, but they're all the same, just different information that's listed on them. And what we want to focus on is carbon's position. All right, so the general periodic tables here, the left-hand and the right-hand columns are slightly cut off on you, so you're not really seeing the full picture, but the majority of it's there. And if I look at carbon, carbon is going to be atomic number 6. Sixth in line from the top. And you read it like a paragraph. 1 starts over here at hydrogen. You can't really see that. 2 goes to helium. 3 is lithium. 4 is beryllium. 5 is boron. And 6 is carbon. So this is the location that we are referring to as far as carbon goes. All right. Now that position is very important, especially in the world of organic chemistry, because that position allows carbon to do a couple of things. And what I want you to keep in mind is look at the group number that carbon is in. Carbon currently is in group number 4, 4A if you're using the new school way, or the Roman numeral 4 with the A after it if you're using the old school way. Doesn't really matter to me. Tomato, tomato, right? So that 4 is pretty important, because in general chemistry, you might have learned about this thing called the octet rule. And octa, or octet, think of octopus. Octopus has 8 legs, or tentacles, right? Well, octet means 8. And what that refers to is that all of the elements on the periodic table, they want 8. 8 what? Well, 8 what we call valence electrons. Again, that's going to be a topic that's going to come down a little bit later on down the train. Not right now. But they want 8. 4 is perfect, because 4 is smack dab in the middle. Look at there. So what that means is that carbon could lose 4 and get 8. What? If you have 4, you're in 4, and you lose 4, how do you get 8? What kind of fuzzy math is this? Well, that again will be explained a little bit later, but carbon could lose the 4 that he has to get the 8, or carbon could gain the 4 that he has to get what we would call the 8, or the octet rule, or full valence electrons. That's what we're really after here. Again, details to come, right? So with this carbon, if he loses or if he gains, doesn't really matter, but one or the other. He can get to this octet rule, or at least be satisfied. Maybe not quite octet, but at least be satisfied with what he has. Because of that, group 4 elements are in a prime position to lose and gain as they please, which makes them a variety pack. Okay, they're not a one-trick pony, people. In other words, if I go to boron, which is right beside of carbon, boron is not smack dab in the middle. He has 3. It would be easier to lose 3 than to gain the 5. Nobody wants to work too hard, do they? It seems like that's kind of the mentality of today's generation of people. Let's work as minimal as possible. Well, boron's the same way. Elements are the same way. Why do I want to gain 5 if I can just lose 3 and be happy? That's what he does. Nitrogen, on the other hand, to the right-hand side of carbon, well, he's in group 5. Well, it's going to be easier for nitrogen to gain 3 than it is to lose the 5 that he currently has. Again, less amount of work. So as you can tell, everything on the periodic table is a one-trick pony. They are forced to do something the same way every time, except for group 4. In group 4, losing 4 or gaining 4, again, smack dab in the middle, you have choice. That choice leads to variety. And those choices and those varieties are wonderful for compounds in organic chemistry. Remember, I told you there's millions of compounds that we can talk about, right? Not only that, but Wohler just told me that these compounds can connect together in different ways to give me different compounds. And we have to have something with a little bit of flexibility in order to do that. Now, the next question that you might have, well, carbon's not the only one in group 4. There's others, and there are. Carbon and silicon and germanium and tin and lead, all of the ones down through here, all of those can flip-flop back and forth. The problem, though, is that as you go down the periodic table, the size gets bigger and bigger and bigger. And that's a problem. If you get too chunky of an element or an atom that comes into play, the size actually does matter in that case. The size will be too big, too bulky for maybe organic chemistry to take place the proper way, and there's problems. So out of the group 4, carbon is primed to be the best. That's because carbon is the smallest. Carbon can get into those little crevices and nooks and crannies that these other atoms cannot do. And that is why he's got the location, location, location. First, he's in group 4. Second, he is the smallest. So therefore, there's not going to be a problem using him later down the road in whatever kind of compound that we are trying to make in the world of organic chemistry. All right, so that's where I'm going to stop this video. In the next video, we'll pick up from this. We'll introduce maybe some general chemistry terms and kind of knock some review into you to see if we can shuffle those files around and loosen up that information that you learned from last semester or maybe last year.